So here we have three geometric series, and these are infinite geometric series x, y, and z. Now we need to show that xz plus yz minus z equals to x times y. So let's begin. So we'll start with the first infinite geometric series x. So x is defined as the summation n going from 0 to infinity. So we have cosine of theta whole raised to the power of 2n. We're going to expand this summation, so this will be equals to, where the first term will be cosine of theta raised to the power of 0, so that's going to be 1. Then we have cosine of theta raised to the power of 2 times 1, so we'll get cosine squared theta. So the third term will be, for n equals to 2, we are going to get cosine of theta raised to the power of 4. And this continues. Now clearly this is an infinite geometric series. Here the first term is 1 and the common ratio is cosine squared theta. So let's note that we have a equals to 1 and the common ratio r is cosine squared theta. We know that whenever we have an infinite geometric series, then the sum to infinite number of terms is given by a divided by 1 minus r. Using this formula, then rx will be equals to 1 divided by 1 minus r. So r is cosine squared theta. Now we know that 1 minus cosine squared theta, that's sine squared theta, which means if we rewrite this equation in terms of sine squared theta, so sine squared theta will be equals to 1 over x. So this becomes equation number 1. So we'll put it aside. Now let's work it. The second infinite geometric series for y, which is given by, in summation n going from 0 to infinity, we have sine phi raised to the power of 2n. So let's expand the summation. The first term was going to be 1, followed by the second term, which will be sine squared phi. Then the third term will be sine raised to the power of 4 phi, and goes on. Here the first term is 1 and the common ratio r is sine squared phi. So using the formula for the sum to infinite series, so we have y equals to 1 divided by 1 minus sine squared phi. So 1 minus sine squared phi, that's cosine squared phi, so we'll get y equals to 1 over cosine squared phi, which means cosine squared phi will then be equals to 1 over y. So this is going to be equation number 2. Then we'll be working with the third infinite geometric series z, which is given by summation n going from 0 to infinity. We have cosine theta raised to the power of 2n times sine phi raised to the power of 2n. When we expand it, we're going to get the first term as 1. The second term is going to be cosine squared theta multiplied to sine squared phi. The third term is going to be cosine raised to the power of 4 theta times sine raised to the power of 4 phi. And this continues. So here the first term, that is 1, and the common ratio r is cosine squared theta times sine squared phi. That means our sum will be, z will be given by 1 divided by 1 minus the common ratio r, which is cosine squared theta times sine squared phi. Right. Now we have already obtained an equation number, so let this be equation number 3. So in equation number 1, we have already obtained the value for sine squared theta. So sine squared theta was given by 1 over x. So from here, we know that cosine squared theta, because we need the value of cosine squared theta, not sine squared theta. Cosine squared theta was just given by 1 minus sine squared theta. The cosine squared theta will be 1 minus 1 over x, or simply x minus 1 divided by x. Then we need the value of sine squared phi. But in equation number 2, we obtained that cosine squared phi, so that came as 1 over y. So if we use the same technique, then sine squared phi will be equals to y minus 1 divided by y. So let's substitute this value back in equation number 3. So our z value will be equals to 1 divided by, so we have 1 minus x minus 1 over x. This is replace in place of cosine squared theta, and sine squared phi will be y minus 1 divided by y. So z will be equals to, so we're going to multiply both numerator and the denominator with xy. So we have xy divided by xy minus x minus 1 times y minus 1. So let's further simplify this. So we're going to get z will be equals to xy divided by xy minus the product of x minus 1 and y minus 1 will be negative xy plus x plus y minus 1. So xy and negative xy gets cancelled, so we are left with z equals to xy divided by x plus y minus 1. Cross multiplying it, this is going to give us zx plus zy minus z equals to x times y, and this is what we were asked to show, hence proved.